Okay, I think we are good to go now. So welcome once again to our main meetup at the Women in Machine Learning and Data Science Accra. So we are a group of young women that are aimed at promoting data science and machine learning. And we usually have this monthly meetups where we talk about different topics. So today we are talking about essential maths for machine learning. And our resource person is Allassan, who is currently a graduate student at the African Masters of Machine Intelligence program, and also the founder of We Do AI. So without further talking, I think we'll just get into it. But meanwhile, while the session is going on, you can feel free to ask any questions in the chat and our resource person will respond to them afterwards. I do hope that you stay with us till the end and actually pick a thing or two from this meetup. Over to you, Allassan.
Thank you for giving me the floor. Evening to everybody, or good morning. So I think I should share my screen.
Yes,
Okay.
you can.
Okay. So can you please see my screen?
Yes, I can.
Okay, thank you. So good evening once more, or good morning to you all. So today we will talk about the essential mathematics for machine learning. I am Allassan Kane, and I'm here to principally present the fundamental of mathematics necessary for the machine learning. Throughout the presentation, I will assume that we have little or no knowledge of mathematics and machine learning. And hopefully with the knowledge that we will learn throughout the presentation, we'll be able to answer some few questions related to mathematics. Related to machine learning using mathematics. So mainly as an about or as an outline, I won't say an outline, but I will principally say it's an about. From my own opinion, I've noticed that machine learning is based on some concept of mathematics, principally linear algebra, calculus, geometry, and probability, which act upon some spaces which are mainly in high dimension to define learning algorithms. So for this particular presentation, we will try to solve a machine learning problem using essential tools of mathematics. I think with this approach, it will be much better for us to understand how important mathematics is for machine learning. And throughout the presentation, we will see how these tools in linear algebra, calculus, geometry, and let's say in probability will be able to help us solve the problem in question. So without wasting a lot of time, let's go to the problem. So let's say we want to perform a lossy compression to a set of points, a set of m points in an n-dimensional space. And we want to perform a lossy compression to these points. Here, the n-dimensional points are represented for this particular example, in 3 dimensions as shown on the figure. And we want to reduce the dimensions such that we are able to have the same points, but in a smaller dimension without much loss of information. So here, for example, we have the points and we have a function that maps those points, the function f of x that maps those points to a space C with a lower dimension. So here the point C, or should I say Ci, belong to a set which has smaller sizes like the initial dimensional space. And we also want to reconstruct the initial points in a high dimension. So like we want to swap from a higher dimension to a smaller dimension, and also want to swap from a smaller dimension back to a higher dimension. And throughout the swapping process, we want to lose a small amount of information as possible. So the main idea here is to reduce the dimension or the size of the points without loss of information. So how can we go about that? So here comes mathematics, and we'll be able to solve this problem, which is a machine learning problem. And once we'll be going throughout the next slides, we will notice that it is a problem that we commonly come across when we work on machine learning, like moving in higher dimension to lower dimension and vice versa. So here we have a function, like I earlier said, f of x, that map all the points in the high dimension to a smaller set or smaller space called, let's say, C. And we also want to define a function G that maps the points from a lower dimension into a high dimension space. But as you notice, there's an approximation sign relating the function G and X, meaning that there might be a loss of information when we go back to the high dimension space. And remember, the objective still is to reduce the information loss as much as possible. So I've been talking throughout about the point X and C, but what actually are these points? So these points are vectors, and vectors are some tools, or should I say some quantities, mainly in physics, that has magnitude and direction. And vectors are mathematically represented as a set of tuples that contains values that are mostly in the set of real numbers, those values. And we can perform some operations to this set of points or sort of vectors such that we can have higher spaces or spaces in higher dimension. So if this set of points are endorsed with some mathematical expressions or mathematical notation, like, for example, addition or multiplication or linear combination, then we can increase the size of those spaces such that we have a vector space in particular. So from a small set of points, we can have larger set of points. And if this set of points are finite, then we can talk of a finite dimensional space. So that's not principally what we are heading on, but it's a basic idea of how we can construct vector space using a set of vectors or set of points called vectors. And now, fortunately for us, or fortunately for mathematicians, they brought up some tools that can help us perform some operation within those vectors. For example, we can scale a vector. Like scaling a vector is simply multiplying the vector with a real number, and that will principally increase the size of the vector. We can perform addition of vectors provided the dimension of the vectors we are adding are the same. We can perform element-wise multiplication of vectors. We can even perform dot product of vectors. And basically, dot product are operations that are performed on vectors, points that have the same dimension, and that will head on to a scalar quantity. So we have a vector, but we end up having a scalar. A scalar in particular could be a real number. We can also measure the size of a vector using what we call a norm. A norm is basically a function that maps a vector to a set of real numbers. And here specifically, introducing the L2 norm, and it helps us also measure the distance between set of points. So this information are not sufficient, but this is enough for us to continue solving our problem. And remember, the problem is to reduce the dimension of those set of points so that we have a small information loss as much as possible. Also, remember that I was talking about a function that mapped those set of points X to another set of points C. And again, we can reconstruct the original space using the function G. So what are actually those functions? They are tools that we call in linear algebra, we call them linear mappings that are transformation that help us change the space or maybe the operations in a set of points from one space to another space. And in our particular case, we are moving from a higher dimensional space, Rn, to a lower dimensional space, let's say Rl, provided the dimension of L is smaller than the dimension of N. And intuitively, we can construct some mathematical properties that we commonly see in mathematics, because reducing the dimension of each of those points from the higher space to a smaller one require us to map each of these points into a space. Like all these points should have a particular image in the smaller dimension. And also the points in the high dimension and in the small dimension should be identical, meaning that each point in the high dimension should map into exactly one point in the smaller dimension. That is a property commonly used in mathematics that we call injectivity. And what it simply means is that if I have a function, a linear mapping from, let's say f in our particular case, that map 2 points to, like, that have two, we have 2 points that the function maps these 2 points to the same image. It means that those points are identical actually. And that's the particular case of our problem. We want to map each of these points into another space where we have those points, but they still preserve their information. And the information in the initial space is that all those points were different. So we'll make sure that they are also different in the smaller dimensional space. So that's the property of injectivity. And again, all the points in the high dimensional space should have an image in the smaller dimensional space and vice versa. Meaning that if I have a set of point X in the space, and in our case, a vector space, we want to map it to a space with a smaller dimension. In our case, it is C. So we can see it from the green arrow heading from the set X to the set C. So all those points should have an image. And that is another property in mathematics that we commonly call as surjectivity. And now combining these two sets of properties, that is injectivity and surjectivity, we have another property called bijectivity. Like if the two conditions are fulfilled, then we can call of a bijective mapping or function. And again, reconstructing this point from the lower dimensional space to a higher dimensional space should fulfill these properties, meaning that if I want to map from C to a point X, each of the points in the space C should be identical to the one in the point X. Like they should be unique and they should all have an image. Okay, so we have this knowledge of the vectors and some properties associated to it. We also have some small knowledge about the functions that, the properties of the function that will help us perform this dimensionality reduction. Then what next? How can we perform this compression actually? So in order to perform the compression, we will want to use a decoding function. The decoding function for our case is one that will reduce the dimension or actually increase it, whatever the case, in whatever the direction we want to move, either using a compression or reconstructing the initial space. And one suitable information we can use to perform the decoding is a matrix. And actually, a matrix, in our case, an n-dimensional matrix, is one which is composed of set of vectors that are arranged in a set of columns, like presented in the notation with the function z. It is actually a matrix that is composed of a different set of vectors. And with this matrix, we can also perform some particular operations like the one in the vectors. And one of those operations could be addition. We can actually scale also a matrix by multiplying it with a real value vector, for example, alpha. We can also perform an identity mapping using an identity matrix that is simply the matrix multiplication of its inverse and the original matrix Z. So these are not all the information that, or all the properties that a matrix could do, but this is sufficient to perform our problem. And I still remember that here we want to perform this compression of points to a smaller dimensional space. Now I've also talked of matrix multiplication with a vector. And this is something very important because once we want to perform a multiplication with a vector, a matrix multiplication with, for example, a vector in a lower dimensional space, then the number of rows of the matrix should be equal to the number of rows here should be equal to the number of columns of, for example, the vector we want to multiply the matrix with. But we want to know why are we using a matrix to perform this compression. So the physical significance of a matrix actually is that once we multiply, let's say, a vector with a matrix, what we are actually doing is a kind of projection. Here in this figure, I'm showing you an example of a 2x2 matrix with the values 1, 0, 0, 0. And now we want to perform a multiplication with a vector, a two-dimensional vector with coordinate 2, 3. And once we perform this multiplication, we have a point 2, 0. But if you want to represent this point in a 2D dimensional space, what we realize is that the points with coordinate 2, 3, when mapped with this matrix or when transformed with this matrix, it is projected in the x-axis. So this is an information that tells us that probably using a matrix and we multiply with the original set of points in the high dimensional space could help us reduce the dimension of the points into a smaller dimensional space. So we might be going toward the right direction when we say we are using the matrix D to perform our lossy compression. All right, so using the matrix is something very nice to do, but there should be some kind of constraint to this particular matrix. Why are we saying so? Because I can use any kind of matrix, for example, and I multiply with a set of points, then I get an output that another matrix will also obtain. So meaning that we can have many solutions if we have many matrices. So this could be a problem because we want to have a unique solution to the lossy compression problem. So how can we have this unique solution? Another particular property of matrices is the property of orthogonality, where we want all the columns of the matrix to be to form a unique norm. Like a norm, if I take 2 columns of the matrix and I compute the norm, for example, the L2 norm to this set of columns, I should have a value 1. With this approach, it is most likely that the matrix or the solution that we will obtain after performing the lossy compression will be unique. And now one physical significance of using an orthogonal matrix is that once we perform a matrix multiplication, obviously, like we saw on the previous image, it helps us have project or the information to a lower dimension. So using an orthogonal matrix also helps us have a direction of a direction that gives us, for example, the higher variance of the informations once projected to a lower dimension. Here it is represented by what we call components. In PCA, for example, we talk of principal components, but let's stop it there and let's just think of the unicity of the solution of the lossy compression using an orthogonal matrix. So remember, we use an inverse matrix, and once multiplied by itself, it gives us an identity. Also, an orthogonal matrix, if we multiply the transpose of an orthogonal matrix with itself, then we also have an identity matrix because the norm of the columns or the rows of an orthogonal matrix will always give us 1. So with this particularity, it will be essential for us to have a unique solution, because if we just use a random set of matrices to multiply with the initial vector points in the vector space, we may have different solutions with different matrices. So remember, we want to have this solution to be unique. And again, we want to reconstruct the information to the higher dimensional space with a unique set of matrices. Okay, so now that using the matrix, we can be able, it is possible for us to reduce the dimension of the points into a lower dimensional space. Is it enough to say that we'll find a solution to reduce the dimension? No, because we want to also make sure that once we reconstruct the information into the high dimensional space, we have the same information as the original space. So we have the matrix D that helps us decompose reduce the dimension of the initial space to a smaller dimension. But we also want this same matrix to help us increase the dimension of this small dimensional space to have the original space. So how can we do that? So one idea that comes into our mind is measuring the distance between the reconstructed vector and the initial vector. So how can we measure it? Remember, we've talked of the norm at the initial slide, where we were able to compute, we use this tool to be able to compute the distance or the size of a vector. So here in particular, we'll be using it to compute the distance between 2 sets of points. And so if the distance is very small, it means that we have been able to reconstruct the information into the original space, for example. The objective here, therefore, would be for us to minimize the distance between the reconstructed vector and the initial vector that we had, so that we'll be able to reconstruct or to get all the information previously in the higher dimensional space. So in order to have this reconstruction property, we are using the L2 norm as initially said. But now the distance between the reconstructed vector and the initial vector should be so small that we will be able to see that the vector X in the higher dimensional space is identical or almost identical to the reconstructed vector. So for that reason, we want to get the set of points that minimizes this distance. And when we talk of the set of points that minimizes this distance, there's a particular property in mathematics or a particular operation that we call the argmin that help us get the set of minimum values that will help us reconstruct the distance or reduce the distance between the set of the reconstructed vector and the higher dimensional vector, like in the original space. So the figure here is a random example of the argmin property or the argmax. Here we have the function sine x of x in red that has a global maximum. The global maximum is actually the site or the point where the function sine x of x attains its very peak value, which is 0 in this case. And notice that sine pi of x or over pi of x also have this same global maximum. So this point 0 could be the argmax for this particular case of the function sine or the family of functions sine k of x over k of x, let's say it like that. So coming back to the problem, minimizing the distance between the reconstructed vector and the initial vector space or the initial set of vector points will require us to look at this particular point where the function x minus g of x in the L2 norm will be able to help us have the small distance as possible. So using the argmin, the argmin function or the L2 norm is actually a square root. So if we use the argmin, and since the L2 norm is monotonically increasing function because it's the square root, so we cannot do the square root of a negative value in our particular case because we are working with real value vectors. So if we square it, we should always get the same argmin value, like the minimum value in our case. Here, the example is about maximum value, but also we'll be talking about the minimum value. So we are looking for the set of points that minimizes this distance. So with the argmin, if we square the L2 norm, we'll still get that same minimum value because, like I earlier said, the L2 norm function is monotonically increasing. So that's the reason why at this particular point, we are squaring the norm, the L2 norm, but we'll still get the same value of C that will minimize this distance. Okay. Remember again that the norm, the L2 norm is the square root of, you see, the X transpose X, because we have been able to show that with the vectors X, we can get its transpose. And once we multiply both of them, we actually have a scalar. And when we square the scalar, that's actually the definition of the L2 norm. So the equation X minus G of C give us the distance between these two sets of points. But once we pass it through the L2 norm, the objective here is to find the minimum value or the minimum value of the minimum value of C that help us minimize this distance per se. So we perform this set of operation like the normal expansion of the function a plus b or the expression a plus b all squared, and we get the third equality where we have X transpose G of C minus G of C transpose X. Actually, the transpose of a vector with itself, or let's say its reconstructed self, is a scalar. So multiplying a scalar or adding X transpose G of C with G of C transpose X will essentially give us the same thing because it is like getting the same scalar in both cases. So we can actually add these two values so that we have something like 2 of X transpose G of C, seen in the simplification section. Yep. And then if we substitute now the value of G of C, yeah, remember G of C was the multiplication of the matrix D and the vector C. So if we substitute it in the next equation, we have C star that is equal to 2 of X transpose times D and C, then the other set of expression. And remember, there's a square in red, which is empty. Why is it empty? Because the value X transpose X, which is a scalar, is independent of C. So it is not necessary for this operation or for the computing that we are about to do. And we will just maintain the information that are essentially variable or variable dependent of C. Remember also that we've talked of orthogonality of a matrix D, and we've talked of the property whereby the multiplication of the matrix D transpose with itself gives us the identity as well. So if we substitute this property to the previous equation, then we have something like C transpose C in the last equality of the simplification section. Okay, so the objective here is to find a set of value of C that minimize the operation negative 2x T transpose DC plus C transpose T times C. Okay, so now that we have that expression, let's talk about something in mathematics called vector calculus, where we want to minimize we want to get the set of value of C that minimize that problem, the aforementioned expression that we had previously. So that is an optimization problem. And in vector calculus, if we are talking about optimization problem, and in our case, a convex optimization problem, we will head into a point where we have a minimum value or a minimum turning point. And there's a property for minimum turning point whereby if we compute the derivative of this turning point or of that turning point, yes, at 0, then we will be able to get a set of points that minimizes that operation or that expression that we had previously. And to perform this operation, we'll be able to use the gradient to obtain this set of value actually. So the minimum turning point in this picture is represented by the green arrow. And at that particular point, the derivative of this function is equal to 0. So why not using this information to compute the value of C that minimizes that distance? So that's what we are doing at the gradient section, where we want to use a gradient over a set of vector operations. And we equate it to 0 to obtain the set of value of C that will help us get the minimum information loss of the reconstruction problem or the lossy compression problem. So we perform the derivative. I've actually skipped 2 steps using this gradient operation function, but we can be able to prove this problem. But based on this gradient operation function, we'll be able to get C star with the green tick that help us obtain, or the set of the C star, the set of vectors that give us the information that help us minimize the reconstruction loss, or the distance that minimizes the reconstruction loss, for example. So if you have this C star, which is D transpose X, then we'll be able to obtain the function that help us map the high dimensional set of points to lower dimension. And now we'll be also able to reconstruct this information, because the reconstruction operation is simply the multiplication of D with C. And so if we substitute that f of x to this reconstruction operation, we'll have the last information, which is D of D transpose X, represented by the green ticks. So we are being able to have the set of information that help us map the function from a high dimensional space to a lower dimensional space. And we have also been able to reconstruct the information loss from the lower dimensional space to the higher dimensional space. So this actually is a problem that we commonly see in principal component analysis, where we perform a lossy compression on a high dimensional space into a space where we can eventually or essentially visualize the points and also recover the information without loss of information as much as possible. So you can notice how using mathematics, essentially, we can be able to solve some machine learning basic problems. And throughout this process, you will notice that we've come across some different tools in mathematics that you will always encounter when you'll be working on machine learning problems. One of them was linear algebra, where we use some tools and some operations using vectors and in high dimensional space in order to perform the lossy compression problem. We also use some notion of geometry. Remember the L2 norm, whereby we were able to measure or quantify the size of the vector and also measure the distance between a set of vectors. We also use the property of gradients that is commonly used in vector calculus in order to get the minimum value of the set of points that minimize this loss of information. For this particular case, we had only one value, which was T star, and we were also able to solve or to define this problem as an optimization problem where we've constrained the matrix D to an orthogonal matrix in order to have a kind of unique solution. So optimization is basically defining some set of constraints in order to get the set of best parameter for a particular problem. And that was actually the case with the minimization that we've been able to perform using the orthogonal matrix. Okay, so this was a mathematical aspect of the essential math for machine learning. But now, how can we head on to, for example, a direct application to of lossy compression using, for example, a machine learning model? So we were talking about PCA here, but now we will move to an application of this PCA into, for example, information compression or data visualization. So I'll stop sharing and I will share another, I'll share now a notebook. Yeah, I think we can all see my screen, and maybe I should increase the size of the notebook. Yes, so I think this is much more clearer. So throughout the theoretical aspect, we're talking about lossy compression, but now let's see how we can head on to an application of this lossy compression in, for example, PCA. And PCA stands here for principal component analysis. And here the objective is essentially to show how we can perform this compression, loss, and this visualization in two-dimensional space. Because in high dimension, it is very difficult to visualize the set of points, for example. So most of the time, what we do is we reduce the dimension of the points into a much more lower dimension without loss of information, or should I say with a small loss of information as much as possible. And also, we will see how important those, the orthogonal matrix that we previously saw during the theoretical aspect of the presentation is important to reconstruct an information into a high dimensional space. So here, I'll start by running this cell, which are just the setup tools that we use for the principal component analysis aspect of this presentation. So here, I start by creating, let me say, a set of random points that we use throughout this process to perform a dimension reduction. So the points are generated randomly using the NP, the NumPy package, let me say like that, and we create 1,000, let me say 200 points, yes, which we generate randomly. And yes, the original set of data that we want to perform a compression to it. Okay. So now, like I earlier said, they're going to perform dimensionality reduction. So let's, for example, say that we fit this set of points using two principal components. I will assume that here we don't know what the principal components are, but you will notice that we've come across it during the theoretical part of the presentation. So if I do that, okay, awesome, I'll have something like this. So here are the principal components as an output, like they are set of vectors. So I have here the first principal component and the second principal component. And I also have the explain variance that I will keep aside and I will explain later. What is important here is the function or the equation U, the expression U, for example, which is actually an orthogonal matrix. Remember the probability of orthogonality that we talked about initially, whereby we set that the norm of the two randomly selected vectors on our matrix will give us 1. That's actually the case here. If you compute the norm of the first principal component and that of the second principal component, you will always head on to get a 1. And to be sure that it is actually orthogonal, we can also perform a dot product between these two sets of vectors, and we'll notice that it is 0, meaning that these points are perpendicular in nature. Like the principal component generate two axes that are actually perpendicular in nature. Talking about the axis, we can actually see the axis also using this cell. For example, if I run them, I'll get something like this. So the long red tail axis is one of these principal components, and the blue one is also another one. So the set of points here also are the randomly generated point that we did previously. And now the objective here is now to perform this compression along one of those axes. You remember when we're multiplying this, the matrix D with the set of points in the high dimensional space to have it in the lower dimensional one. So these axes help us perform this compression. And it will favor a direction where we have the highest variance as much as possible. So imagine compressing this point along the red axis. In that case, we will have a high variance. Why? Because the points will be spread apart as much as possible. Whereas if we perform the compression along the blue one, the point will be congested along this axis. The variance in that case will be very low. It means that we are losing many information that were available in the high dimensional space. So let's try to do this compression. Okay. So here, if we perform the compression, you'll notice that the shaded points that are strongly shaded are actually the points, the compressed point or the projected point along the red axis, and the lighted blue points are the ones, the original set of points in the higher dimension. So you see that here we are projecting from a two-dimensional space to a one-dimensional space that is along the red axis. And you notice that if we project along the red axis, yeah, it is possible for us to have a very high amount of variance. And that's very important when we perform principal component analysis, whereby we want to project the points where we have as much variance as possible. So that's actually the case. And let's try to see how we can apply it to a set of points that we commonly know, for example, in the scikit-learn package. And for this particular case, we have the low-D data set that contains images of numbers from 0 to 9, sorry. And we'll see how we can perform this compression of information, or this visualization of information using principal component analysis. So if I run this cell with two-dimensional components here, you see that we are reducing the dimension of the set of points from 64 to 62. For example, here, we have the dimension have been reduced from 64 to 62. And it is very important, or it is very good for us to have this projection in lower dimension, because we'll be able to visualize it much more clear. Because you see, the different set of points that are represented by different colors actually represents numbers from 0 to 9. And we can actually see how they are spread apart, and they try to form some set of clusters amongst one another. And here, this is something that is good for visualization also. So now let's think of doing, choosing the number of components, for example. Throughout this running of notebook session, we have been presenting only some components, and maybe we want to understand the variance that we obtain after projecting this information to lower dimension, like using this different set of components. Because remember, the information that we want to obtain to preserve as much variance as possible. So this graph actually shows us how the number of components vary with the cumulative variance. So for example, if the number of components, let's say, is from 0 to 10, let's say, you see that the variance here is very small, whereas the cumulative variance keep on increasing until it reaches a value of 1 when we are approximately at 64. Look at the squared curve, if I could say like that. You will notice that the curve ends at the value 64, and at that particular point, the variance is 1. So it means that with all the number of components, we can be able to reconstruct exactly the same information that we had when we were in the high dimensional space, for example. So this gives us an information that with the reduced dimension or the reduced number of components, it is possible for us not to have all the information as we had earlier in the high dimensional space. So the problem that we were able to solve theoretically with just, for example, 2 number of components will not be suitable in practical application, for example. So it is very important to have an idea of how the principal components or how the points are spread across a different set of principal components. So if you want to check, for example, the number of variance or the cumulative variance for each set of components, you notice that at the component number 0 or the first principal component, the variance is something like 0.15. But as we go on to higher components, or as we take into consideration all the other set of components, you will notice that the set of variance or the explained variance increases to something like 1, which backs the point that we were previously explaining, that using all the set of components help us have the total set of variance. Okay, so now let's try to perform what we call data compression. So this is actually the problem that we will try to solve on the theoretical approach, and let's see how it actually perform what we wanted to do. So this image, or this widget, if I should say it like that, represents 2 points. The first one is an image in a lower dimensional space. You see, in this particular case, where K is 1, it is because we just have one principal component that we take into consideration to perform this projection. And the second image is the original data point. Now, we want to reconstruct, like we previously saw, the original information. But you've noticed that with only one number of components, it is very difficult for us to be able to have the original data. So let's think of increasing maybe the number of components to, let's say, 9. And you see that the constructed information, or the projected information, turns to becomes essentially similar to the original data or the original image. Let's increase it again, maybe to 30 number of principal components. You see that the point becomes much more closer to the image, the original image in this space. So this gives us an information that changing the points or the number of components, from, let's say, 1 to 30, or increasing the number of components, will help us increase the accuracy of the reconstruction of the information to the higher dimensional space. So, but this will be kind of difficult when we want to represent the values or the points in high dimension, because it will not be feasible for us to actually identify some patterns around this set of points. So this is actually how we can perform some lossy compression from a higher dimensional space to a lower dimensional space, or maybe a reconstruction from a lower dimensional space to a higher dimensional space. We can also take another example whereby I can take, for example, 3, and you see that the approximated image of 3, let's say, is identically similar to the original image. But if you try to reduce the dimension, let's say to, let's say, 4, you notice that it is kind of blurred and we cannot actually identify the different information. So that was it for the problem of lossy compression. And I hope that with this problem, we've been able to cover at least the shallow aspect of the mathematics that are essential for the machine learning. So thank you for your kind attention, and I'm open for different set of questions. Thank you.
Thank you very much, Allassan. That was a very interesting and detailed presentation. So we'll just wait a few minutes. If anyone has any question, please feel free to put it in the chat, or you can just unmute and then ask your question. Okay, so we have one question, actually some few questions in the chat. So one says that how do you use the geometry parts in machine learning?
Okay, thank you for this question. The geometry part in machine learning in this particular case was essentially used on a property of norms, because we use the norms to actually measure the distance between the points that were reconstructed and the points in the original vector space. So remember, we were reducing the dimension from a higher dimensional space to a lower one, and we're also able to reconstruct the points from a lower dimension to a higher dimension. But once we reconstruct these points to a higher dimension, we want to verify that those points actually maintain, let me say, the same position like they were in the original dimensional space. In order to do that, we want to measure the distance between the set of points. And also, we will even want to measure maybe the angle between the reconstructed points and the points in the original space. That was not done during this presentation, but that's also a property of geometry that we could use to verify that those points actually are maintaining the same position. So for example, if the angle between that point and the reconstructed point was, let's say 0 or 180, then means that the mapping from the small dimensional space to a higher one was something that was quite accurate. So that's maybe how we can use extend geometry to this problem.
Okay. So we have another question by Caleb. He says, please, what type of machine learning algorithm was used?
Yes, so the machine learning algorithm that we use in this case was not really a machine learning algorithm, but it was a kind of dimensionality reduction algorithm, and it was principal component analysis.
Okay, thank you very much, Allassan. So without any further questions, I think this brings us to the end of the session. Oh, okay, there's actually one question that says, please, do you have to learn the mathematics behind machine learning before you start studying machine learning?
Okay, thanks for the question. Yes, for this question, this is my opinion, but I would say you can learn both at the same time. Like you can read maybe some machine learning books and you want to better understand how the algorithm works. And in order to understand how they do, you will need some essential mathematics for machine learning. And so for this reason, I will advise you to go along with both mathematics and machine learning when you are doing your reading process or your studying process for machine learning. It will really help you.
Okay, so I think what I would just like to add is that anyone can just go and use libraries for like any machine learning problem. But if you actually understand the mathematics behind the libraries you are using, then it's very easier for you to debug your codes. Like anytime you encounter an error, you already know how it was built and how the library works. So that way it's easier for you to trace back in and solve that error. And I think this would help. And the last question we have is, what book do you recommend for machine learning?
Oh, okay. So for me personally, and I think that will help everybody, the book I usually recommend for machine learning is the the deep learning and machine learning book by Aaron Colville, Joshua Benjo, and Jan Goodfellow. It is an open access book in the MIT Press. So you can get all the notions of mathematics that heads you into machine learning directly from there. I can share the link to the book if you want it.
Okay, I think there's another book by Bishops, which is pattern and recognition and machine learning. So that is also there. So please don't forget to join our Telegram and our Meetup page for more meetups like this. And also don't forget to follow Allassan on Twitter and also the WiMLDS Accra chapter on Twitter. So I just put the names that we use on there so that you can easily follow for more information. And once again, thank you everyone for joining this session, and we are hoping to see you in our next session. Also, thank you very much, Allassan, for giving us this detailed presentation. Bye, everyone.
Bye.